What if the newest interstellar visitor racing through our solar system right now, a mysterious object called 3I Atlas, suddenly broke apart before our eyes, revealing secrets from another star system that have been frozen for billions of years? What if this cosmic time capsule, traveling faster than any previous interstellar visitor, holds the key to understanding how alien worlds form? And what conditions exist in the depths of space, between the stars? Tonight, as you drift into the cosmic mysteries surrounding us, we're going to explore what would happen if 3I Atlas fragmented during its closest approach to the Sun, and what incredible revelations about distant worlds and cosmic history might spill out into the void. This isn't just science fiction, it's happening right now, and astronomers are watching with the most powerful telescopes ever built. Before we dive into this extraordinary cosmic investigation, make sure you are subscribed, because what we discover inside this interstellar wanderer could revolutionize our understanding of planetary formation, alien chemistry, and the hidden processes that shape worlds around distant stars. Hurriedly, let's begin our investigation by meeting the most remarkable cosmic visitor to enter our solar system since we began watching the skies. An object so unusual that it's forcing scientists to reconsider everything they thought they knew about interstellar space. On July 1st, 2025, the Atlas Survey Telescope in Chile captured something extraordinary moving against the background stars, a faint point of light racing through our solar system at nearly twice the velocity of any previous interstellar visitor. NASA missions are working together to track and study this rare, interstellar comet as it passes through our solar system, and what they've discovered has shaken the astronomical community. This is 3I Atlas, the third confirmed interstellar object ever detected passing through our cosmic neighborhood, and it's unlike anything we've encountered before. While Oumuamua puzzled us with its strange acceleration, and Borisov appeared reassuringly comet-like, 3I Atlas combines the familiar with the utterly alien in ways that challenge our understanding of what interstellar space contains. The object's speed is staggering. 3I Atlas has the highest eccentricity of the three interstellar objects known to date, greater than 1I Oumuamua's, EP 1.2, and 2TI Borisov's, EP 3.4. This hyperbolic trajectory speaks of an origin so distant that the object has been traveling through the cold emptiness between stars for potentially billions of years before arriving in our solar system. As 3I Atlas raced inward toward the Sun, astronomers noticed something that immediately set it apart from typical comets. During September's total lunar eclipse, astronomers captured rare images of interstellar comet 3I Atlas glowing green, suggesting more about its chemistry. This ethereal green glow indicates the presence of diatomic carbon molecules, a chemical signature that provides our first clues about the alien chemistry contained within this cosmic visitor. But the green glow is just the beginning of 3I Atlas's mysteries. The earliest images of 3I Atlas, newly uncovered by Michigan State University, reveal how the interstellar object evolved as it traveled through our solar system, and how other distant solar systems might be different from our own. These observations show an object that's not just passing through our solar system, but actively changing as it encounters the increasing warmth and radiation of our Sun. As we observe 3I Atlas during its approach, we're witnessing something unprecedented. An examination of the interstellar object 3IA Atlas shows that it is likely to be a remnant of the galaxy's cosmic noon, period circa 9 to 13 billion years ago. This timing is extraordinary, suggesting that the object carries within its frozen interior materials that formed when our galaxy was young and star formation was at its peak. The implications are staggering. 3I Atlas isn't just a visitor from another star system. It's a messenger from cosmic antiquity, carrying preserved samples of conditions that existed when the Milky Way was in its stellar infancy. The materials locked within its nucleus might represent chemistry from an era when the first generation of heavy elements was being forged in the cores of massive stars. But what makes 3I Atlas truly remarkable is what might happen as it approaches its closest point to the Sun. 3I Atlas will come closest to the Sun on 29th of October 2025 at 11:44 plus 00.1 UT. The comet's perihelion, or closest distance to the Sun, is 1.36 astronomical units, closer than Mars but farther than Earth, a distance where the Sun's heat becomes intense enough to trigger dramatic changes in cometary nuclei. Historical precedent suggests that interstellar comets face unique stresses during their solar encounters. As 3I Atlas comes closer to the Sun, where the comet suddenly ejects a large amount of dust and brightens, or even fragmentation events, where the comet's nucleus breaks into pieces like what happened with the previous interstellar comet, 2I Borisov. The mention of Borisov as fragmentation is particularly significant. We've already seen one interstellar visitor break apart during its solar encounter. The physical stresses on 3I Atlas are immense. After potentially billions of years in the near absolute zero of interstellar space, the object is now experiencing rapid heating as it approaches the Sun. Different materials within its nucleus will respond differently to this thermal stress, some expanding, others contracting, creating internal pressures that could literally tear the object apart. But unlike comets from our own solar system, which have had billions of years to settle into equilibrium with our Sun's influence, interstellar visitors like 3I Atlas are experiencing solar heating for the first time in their existence. The materials within the nucleus have never been subjected to the kind of thermal cycling that shapes objects in our solar system, making their response to solar heating unpredictable and potentially catastrophic. As you contemplate this cosmic drama unfolding in real time, consider that we might be witnessing one of the universe's most spectacular archaeology projects. If 3I Atlas fragments during its solar approach, it would be like opening a time capsule that has been sealed since the galaxy's youth, revealing pristine samples of alien chemistry that have been preserved in the cosmic deep freeze for eons. But what exactly would we discover if 3I Atlas broke apart? What alien chemistry and ancient materials might spill out into space? And how would we study them with our most advanced telescopes? As we delve deeper into the mystery of what lies within 3I Atlas, we encounter chemistry so alien that it challenges our understanding of how planetary systems form around other stars. The green glow that astronomers have already detected is just the beginning. Inside this interstellar visitor lies a chemical composition that might rewrite our textbooks on cosmic chemistry. When scientists analyze the light coming from 3I Atlas using spectroscopy, they're essentially performing cosmic chemistry from a distance of millions of kilometers. The green glow that makes this comet so distinctive comes from diatomic carbon molecules, C2 being excited by solar radiation. But this is just the outermost layer of the chemical onion that makes up this interstellar visitor. Not only was it made of carbon dioxide, but it had a carbon dioxide ice-to-water ice ratio that was literally out of this world, 8:1, which is among the highest ever recorded. It offers a potential glimpse into the conditions that exist in other solar systems and how those systems formed. This extraordinary chemical composition immediately sets 3I Atlas apart from anything we've seen before. To understand why this chemistry is so significant, we need to consider how comets form in planetary systems. In our solar system, comets condensed from the same nebular disk that gave birth to our planets about 4.6 billion years ago. The ratios of different ices, water, carbon dioxide, carbon monoxide, and various organic compounds reflect the temperature and pressure conditions in different regions of our primordial solar system. But 3I Atlas formed around an alien star, under conditions that were clearly very different from our own system's birth environment. The 8:1 ratio of carbon dioxide to water ice suggests formation in a region where carbon dioxide could condense more readily than water. Perhaps in the outer reaches of an alien solar system where temperatures were so low that CO2 froze out before water vapor could condense. This chemical signature tells a story about an alien world's formation that differs fundamentally from our own. The star system where 3I Atlas originated might have been carbon-rich compared to our Sun, or the protoplanetary disk might have had a different temperature profile that favored carbon dioxide formation over water ice. Each of these possibilities opens windows into understanding how planetary systems can evolve along pathways completely different from our own. The NASA FEI-CSA James Webb Space Telescope observed interstellar comet 3I Atlas on 6th August 2025 using its near-infrared spectrograph. The research team is analyzing Webb's data, with a preprint now available online. The James Webb Space Telescope's observations are revealing chemical details that were impossible to detect with previous instruments, potentially uncovering molecular signatures that have never been seen in any solar system object. If 3I Atlas were to fragment during its solar approach, the resulting debris cloud would create an unprecedented opportunity to study alien chemistry in detail. The fragmentation would expose fresh interior materials that have been shielded from space weathering and cosmic radiation for billions of years. These pristine samples would reveal the original chemistry of the alien protoplanetary disk, where 3I Atlas formed. Imagine the scientific bonanza that would result from such a fragmentation event. Instead of observing just the surface materials that have been altered by eons of exposure to interstellar radiation and cosmic rays, we would suddenly have access to the chemically unaltered core of an interstellar object. It would be like being able to study the interior of an alien world without ever leaving our solar system. The fragmentation process itself would reveal the object's internal structure in ways that external observations cannot. Different layers within the nucleus would respond differently to thermal stress, potentially creating a stratified debris field where materials from different formation periods and locations within the original protoplanetary disk could be studied separately. But the alien chemistry within 3I Atlas might extend far beyond simple ice compositions. The object could contain organic compounds that formed under conditions completely different from anything in our solar system. These alien organics might follow chemical pathways that don't exist on Earth, potentially revealing new approaches to complex chemistry that could inform our understanding of how life might arise in very different environments. The possibility becomes even more intriguing when we consider the object's extreme age. An examination of the interstellar object 3I Atlas shows that it is likely to be a remnant of the galaxy Ceti 9's cosmic noon period, circa 9 to 13 billion years ago. This means the chemistry within 3I Atlas predates our entire solar system by billions of years, potentially preserving chemical signatures from an era when the galaxy's chemical composition was very different from today. During the galaxy's cosmic noon period, star formation rates were at their peak, and the first generations of massive stars were producing and distributing heavy elements throughout the galaxy. The interstellar medium had a different chemical composition then, and planetary systems forming during that era would have incorporated elements in ratios very different from what we see today. 3I Atlas might contain isotopic ratios of various elements that reflect this ancient galactic chemistry. These isotopic signatures could provide insights not just into how the object's parent star system formed, but into the chemical evolution of the galaxy itself during one of the most important periods in cosmic history. The thermal processing that would occur during fragmentation could also reveal chemical compounds that remain stable only under extreme conditions. As different parts of the nucleus heat up at different rates, we might observe chemical reactions that don't occur naturally in our solar system, providing insights into exotic chemistry that requires specific combinations of temperature, pressure, and composition to manifest. As you contemplate these possibilities, consider that a fragmentation event would transform 3I Atlas from a single mysterious object into a distributed laboratory where dozens or hundreds of separate chunks could be studied individually. Each fragment would tell part of the story about alien world formation, ancient galactic chemistry, and the processes that have shaped the cosmos for billions of years. But the chemical revelations would be just the beginning. If 3I Atlas fragmented, what would the internal structure tell us about how objects form in alien solar systems? And what new insights would we gain about planetary formation processes throughout the galaxy? As we continue our exploration of what 3I Atlas might reveal if it broke apart, we venture into one of the most fascinating aspects of this cosmic visitor: its internal structure. This isn't just about chemistry frozen in ice. It's about the physical architecture of how materials organize themselves during planetary formation in alien solar systems. When we study comets from our own solar system, we've learned that they're far from uniform chunks of ice and rock. Instead, they're complex, layered structures that preserve a detailed record of how our solar system formed. The way materials are distributed within a comet's nucleus tells the story of temperature gradients, chemical processes, and physical forces that operated during the formation of our planetary system. But 3I Atlas formed in an alien environment, under conditions that might have been radically different from our own solar system's birth. If this interstellar visitor fragmented during its approach to the Sun, we would get our first detailed look at how planetary formation processes operate around other stars. And the results might be completely unlike anything we've seen before. The extreme velocity of 3I Atlas provides our first clue about its structural properties. Objects traveling at such tremendous speeds through interstellar space are subject to unique physical stresses that do not affect objects within solar systems. For billions of years, 3I Atlas has been bombarded by cosmic rays, struck by microscopic interstellar dust grains, and subjected to the subtle but persistent pressure of starlight from distant suns. The microscopic breakup of the surface to supermicron fragments by interstellar impactors, such as dust gas and cosmic ray particles, might have led over billions of years to the formation of large dust particles that are released close to the Sun and account for the glow ahead of 3I Atlas. This suggests that the object's surface has been fundamentally altered by its journey through interstellar space, creating a weathered outer layer that might be very different from its pristine interior. If 3I Atlas fragmented, we would suddenly have access to materials that have been protected from space weathering for eons. The contrast between the weathered exterior and the pristine interior would reveal not just the original structure of the object, but also the processes that alter materials during billion-year journeys through the cosmos. The internal structure of 3I Atlas might reveal layering patterns that reflect the conditions in its parent protoplanetary disk. Different layers could represent different epochs of formation, when various materials condensed out of the cooling disk at different distances from the alien star. These layers might be organized in ways completely different from what we see in our solar system's comets, revealing alternative pathways for planetary system formation. Consider the possibility that 3I Atlas formed in a protoplanetary disk where the temperature and pressure gradients were inverted compared to our own solar system. Instead of increasing temperature toward the center, the alien system might have had complex temperature patterns created by multiple stars, unusual stellar evolution, or exotic heating mechanisms that we've never observed. The resulting structural patterns within 3I Atlas would preserve evidence of these alien formation conditions. The object's nucleus might also contain structural features that reveal the gravitational environment where it formed. If 3I Atlas originated in a binary star system or in the outer regions of a massive planetary system dominated by giant planets, the tidal forces during formation would have created internal structures very different from those found in objects that formed in our relatively simple single-star environment. But perhaps most intriguingly, the fragmentation of 3I Atlas might reveal whether the object contains any artificial structures. While this remains highly speculative, the possibility cannot be entirely dismissed. If an advanced alien civilization had embedded monitoring devices, data storage systems, or other technological artifacts within what appears to be a natural comet, fragmentation would be the only way to discover such hidden elements. The density distribution within 3I Atlas, revealed through fragmentation patterns, could also tell us about the mechanical properties of materials formed in alien environments. Different gravitational conditions, radiation environments, and chemical compositions could create materials with properties that don't exist anywhere in our solar system. These alien materials might have unusual strength, flexibility, or thermal properties that could inform our understanding of materials science under extreme conditions. The way 3I Atlas breaks apart would also reveal the stress patterns within its structure. If the object fragments along natural grain boundaries that formed during its original accretion, we could study how materials clump together under alien gravitational and thermal conditions. If it breaks due to thermal stress, creating new fracture patterns, we could learn about the thermal properties of alien ices and how they respond to solar heating. The size distribution of fragments would provide insights into the scale of structural organization within the nucleus. Large fragments would preserve information about major structural divisions, while smaller pieces would reveal details about how materials are organized at microscopic scales. Each size range would tell part of the story about how complex structures self-organize during planetary formation processes. The fragmentation event might also reveal whether 3I Atlas contains any void spaces or hollow regions within its interior. Such voids could form through several mechanisms: sublimation of volatile materials during the object's formation, gravitational settling that creates density differences, or even biological processes if life existed in the alien system where the object formed. As you contemplate these structural mysteries, consider that each fragment of a broken 3I Atlas would be like a piece of an alien jigsaw puzzle. By studying how the pieces fit together and analyzing the interfaces between different structural regions, scientists could reconstruct not just the object's internal architecture, but the sequence of processes that created that architecture billions of years ago in a star system we may never be able to visit. But beyond structure and chemistry, a fragmented 3I Atlas might reveal something even more extraordinary: evidence of the physical processes that have shaped our galaxy for billions of years, and clues about cosmic evolution that we could never discover any other way. As we drift deeper into the profound implications of what 3I Atlas might reveal, we encounter perhaps the most extraordinary aspect of this cosmic visitor: its potential role as a messenger from one of the most important periods in galactic history. If this object fragments during its solar encounter, it might release information that could revolutionize our understanding of how the entire Milky Way galaxy evolved during its most dynamic period. An examination of the interstellar object 3I Atlas shows that it is likely to be a remnant of the galaxy's cosmic noon period, circa 9 to 13 billion years ago. This timing places the object's formation during the most crucial epoch in our galaxy's development, when star formation was at its absolute peak and the chemical composition of the entire Milky Way was being established. To understand the significance of this timing, we need to appreciate what cosmic noon represents in galactic evolution. This was the period when our galaxy was forming stars at a rate 10 times faster than today, when the first generations of massive stars were ending their lives in spectacular supernovae. and when the heavy elements that make planets and life possible were being forged and distributed throughout galactic space. If 3I Atlas truly originated during this period, then the materials within its nucleus represent a frozen sample of galactic conditions from an era we can study in no other way. While we can observe distant galaxies to see what cosmic noon looked like in other parts of the universe, we have no direct samples of what our own galaxy was like during this crucial period. Until now, the fragmentation of 3I Atlas would release materials that have been preserved in the cosmic deep freeze for over 9 billion years. These aren't just alien materials from another star system. They're ancient materials that formed when the galaxy itself was young and chemically different from today. The isotopic ratios of elements within these materials would provide direct evidence of the nuclear processes that were operating in massive stars during cosmic noon. During this period, the interstellar medium, the gas and dust between stars, had a very different chemical composition than it does today. The first generation of stars had begun producing heavy elements, but the mixing processes that would eventually create the relatively uniform chemical composition we see in our local galactic neighborhood were still ongoing. Star-forming regions during cosmic noon would have had dramatic chemical gradients and exotic element ratios that no longer exist anywhere in the nearby galaxy. 3II Atlas could preserve evidence of these ancient chemical conditions. If the object formed in a star-forming region that was enriched by the supernova of a particularly massive first-generation star, it might contain isotopic signatures that reflect the unique nuclear processes occurring in stars that were fundamentally different from any that exist today. But the revelations could extend beyond simple chemistry to encompass the physics of star and planet formation under very different galactic conditions. During cosmic noon, the galaxy's spiral structure was less well-defined, the central supermassive black hole was more active, and the overall density of stars and gas was much higher than today. These different conditions would have created star-forming environments unlike anything we observe in the contemporary galaxy. The way materials are organized within 3I Atlas's nucleus might reflect these ancient formation conditions. If the object formed in a dense stellar cluster during cosmic noon, the gravitational influences from nearby massive stars would have created tidal effects and heating patterns completely different from the isolated conditions where most comets in our solar system formed. The fragmentation event might reveal layered structures within 3I Atlas that record the history of multiple star formation episodes in its birth region. Each layer could represent materials that condensed during different periods of stellar activity, creating a kind of geological record of ancient star formation processes. By studying these layers in sequence, we could reconstruct the timeline of stellar evolution in the object's birth environment. The object might also contain materials that formed under the influence of different stellar populations than exist today. During cosmic noon, the galaxy contained more massive stars, more active galactic nuclei, and more energetic stellar feedback processes. These conditions would have created unique high-energy environments where exotic chemical and nuclear processes could occur. If 3I Atlas contains materials that formed under intense radiation environments, or in regions where stellar winds from massive stars created unusual pressure and temperature conditions, these materials might have properties that cannot be replicated in any contemporary astrophysical environment. They would be literally impossible to study, except through samples preserved from cosmic noon. The magnetic properties of materials within 3I Atlas could also reveal information about the galactic magnetic field during cosmic noon. The galaxy's magnetic field has evolved significantly over billions of years, and materials that formed during this ancient period might preserve magnetic signatures that record the field's strength and configuration when the galaxy was young. Even the organic chemistry within 3I Atlas, if any exists, would reflect the different conditions for complex molecule formation that existed during cosmic noon. The higher radiation levels, different stellar populations, and more active galactic environment would have created pathways for organic synthesis that might not exist in the contemporary galaxy. As you contemplate the profound implications of studying materials from cosmic noon, consider that 3I Atlas might be our only direct link to understanding how our galaxy developed the conditions that eventually made the formation of our solar system, our planet, and ultimately our existence possible. The object carries within its frozen interior a record of the cosmic processes that set the stage for everything that followed in galactic history. But perhaps the most mind-expanding possibility is what 3I Atlas might reveal about the prevalence of planetary systems throughout the galaxy, and whether the conditions that created our solar system are common or extraordinarily rare in the cosmic scheme. As we continue our investigation into what 3I Atlas might reveal if it fragmented, we approach one of the most profound questions in astronomy. How common are planetary systems like our own? And what do the materials within this interstellar visitor tell us about the diversity of worlds that exist throughout the galaxy? Every piece of material within 3I Atlas carries information about the planetary system where it formed. The chemical composition, isotopic ratios, and structural properties don't just tell us about the object itself. They provide a direct window into understanding an entire alien solar system that existed billions of years ago. Interstellar objects like 3I Atlas that have been captured in planet-forming disks around young stars could become the seeds of giant planets. This observation points to a fascinating possibility that objects like 3I Atlas might not just be products of planetary formation, but active participants in the process, carrying materials between star systems and potentially seeding the formation of new worlds. The chemical signature of 3I Atlas, with its extreme carbon dioxide to water ice ratio of 8:1, immediately tells us that its parent system was chemically very different from our own. In our solar system, water ice dominates the composition of outer system objects, reflecting the temperature and chemical conditions that existed in our protoplanetary disk. But the alien system where 3I Atlas formed clearly had a very different chemical environment. This difference might reflect several possible scenarios about the alien world's formation. The parent star might have been more carbon-rich than our Sun, leading to higher concentrations of carbon-bearing molecules in the protoplanetary disk. Alternatively, the system might have formed in a region of the galaxy where the interstellar medium had a different chemical composition than the region where our Sun formed. But perhaps most intriguingly, the chemical signature might reflect the influence of giant planets in the alien system. In our solar system, Jupiter's gravitational influence significantly affected the distribution of materials throughout the outer solar system. If 3I Atlas formed in a system with giant planets in different locations or with different masses than our gas giants, the resulting chemical distribution would be completely different. The fragmentation of 3I Atlas would reveal whether the object contains materials that formed at different distances from its parent star. Different temperature zones in the protoplanetary disk would have produced materials with distinct chemical signatures. By analyzing fragments with different compositions, we could potentially reconstruct the temperature profile of the entire alien planetary system. This temperature reconstruction could reveal whether the alien system had a habitable zone, a region where liquid water could exist on planetary surfaces. If 3I Atlas contains materials that formed in temperature ranges consistent with liquid water, it might indicate that the parent system was capable of supporting Earth-like worlds. But the implications extend far beyond simple habitability. The way materials are organized within 3I Atlas might reveal whether the alien system contained rocky terrestrial planets, gas giants, or exotic planetary types that don't exist in our solar system. Different planetary configurations create different patterns of material distribution that would be preserved in the structure of objects like 3I Atlas. The object might even contain materials that were processed by passing close to alien planets during its formation. If 3I Atlas originated as part of a larger body that was disrupted by gravitational encounters with planets in its home system, the fragmentation patterns and material compositions would carry signatures of those ancient planetary encounters. The age of 3I Atlas, tracing back to cosmic noon, means that it formed during a period when planetary systems throughout the galaxy might have been very different from contemporary ones. The higher star formation rates, different stellar populations, and more active galactic environment during that period would have created conditions for planetary formation that might not exist anywhere in the galaxy today. If 3I Atlas contains materials from this ancient epoch of planetary formation, fragmentation would provide our only direct samples of what early planetary systems were like. These materials might reveal whether planets formed more quickly or slowly during cosmic noon, whether they achieved greater masses due to the higher availability of heavy elements, or whether they followed entirely different evolutionary pathways than planets forming today. The organic chemistry within 3I Atlas, if it exists, would be particularly revealing about the potential for life in alien systems. Complex organic molecules require specific temperature, pressure, and chemical conditions to form and remain stable. The presence or absence of such molecules within 3I Atlas would indicate whether its parent system had regions where the chemistry of life could develop. But even more significantly, the specific types of organic molecules could reveal whether alien biochemistry follows the same pathways as terrestrial life, or whether completely different approaches to complex chemistry are possible. This information would fundamentally inform our understanding of how common life might be throughout the galaxy. The physical properties of materials within 3I Atlas would also reveal information about the mechanical environment in its parent system. Materials formed under different gravitational conditions, radiation environments, or magnetic field strengths would have distinct physical characteristics that could be identified through careful analysis of fragments. These physical properties might reveal whether the alien system contained unusual features, perhaps multiple stars creating complex gravitational environments, or massive planets generating strong magnetic fields that influenced material formation throughout the system. Each unusual feature would leave its signature in the materials that eventually became incorporated into 3I Atlas. As you contemplate these possibilities, consider that 3I Atlas might be carrying within its nucleus a complete archive of information about an alien solar system that existed when our galaxy was young. Every fragment released by a potential breakup would be like a page from this cosmic library, revealing details about worlds and conditions that we could never observe directly, but that expand our understanding of the incredible diversity of planetary systems that exist throughout the cosmos. This brings us to one of the most exciting aspects of studying 3I Atlas: what its fragmentation might reveal about the processes that connect star systems across the galaxy, and how objects like this might actually facilitate the spread of materials, information, and perhaps even life between distant worlds. As we delve deeper into the implications of 3I Atlas and what its fragmentation might reveal, we encounter one of the most fascinating concepts in modern astronomy: the idea that interstellar space might be filled with a vast transport network that moves materials, information, and potentially even life between star systems across the galaxy. Traditional astronomy has always viewed star systems as isolated islands in the cosmic ocean, separated by such vast distances that meaningful exchange between them seemed impossible. But objects like 3I Atlas are forcing us to reconsider this perspective, revealing that the galaxy might be far more interconnected than we ever imagined. The mere existence of 3I Atlas proves that materials can and do travel between star systems. But this isn't just about one unusual object making an extraordinary journey. It might represent just one visible example of a vast, ongoing process that has been operating throughout galactic history. If interstellar visitors like 3I Atlas are common, then the galaxy might contain a continuous circulation system that moves materials between stellar systems like a cosmic bloodstream. The fragmentation of 3I Atlas would provide crucial insights into how this transport network operates. The way the object responds to thermal stress, the composition of materials released during breakup, and the distribution patterns of fragments would all provide clues about the physical processes that govern interstellar material transport. Consider the possibility that 3I Atlas isn't just a random chunk of ice and rock that happened to escape its home system, but part of a systematic process that operates throughout the galaxy. During the violent early stages of planetary system formation, countless objects are ejected from their birth systems through gravitational interactions with forming planets. These ejected objects don't simply disappear, they become part of a vast population of interstellar wanderers. Some of these wanderers eventually encounter other star systems, where they might be captured and incorporated into new planetary systems. Interstellar objects like 3I Atlas that have been captured in planet-forming disks around young stars could become the seeds of giant planets. This process creates a mechanism for material exchange between star systems that has been operating for billions of years. The implications of this transport network are staggering. If materials regularly flow between star systems, then the chemical evolution of the galaxy becomes much more complex and interconnected than traditional models suggest. Elements forged in massive stars don't just enrich their local interstellar neighborhoods. They can be transported across vast distances and incorporated into planetary systems that form much later and much farther away. 3I Atlas might carry within its nucleus samples of materials from multiple star systems. During its billion-year journey through interstellar space, the object might have encountered and incorporated materials from other interstellar visitors, creating a kind of cosmic sampling device that collects materials from throughout the galaxy. The fragmentation of such an object would release this collected material for study, potentially providing samples from dozens of different stellar environments. Each type of material could be analyzed to determine its origin, creating a map of the galactic regions that 3I Atlas has encountered during its journey. But the transport network might carry more than just inorganic materials. If complex organic molecules can survive the journey between star systems, then interstellar visitors like 3I Atlas might be transporting the chemical precursors of life throughout the galaxy. This process, known as panspermia, could create connections between the origin of life on different worlds. The organic chemistry within 3I Atlas, revealed through fragmentation, would provide crucial evidence about the viability of interstellar panspermia. Complex organic molecules that have survived billions of years in the cosmic deep freeze would demonstrate that the chemical building blocks of life can indeed travel between star systems while maintaining their structural integrity. Even more speculatively, if life itself can survive interstellar journeys, then objects like 3I Atlas might be carrying living organisms or their preserved remains. While the harsh conditions of interstellar space make this seem unlikely, certain extremophile organisms on Earth have demonstrated remarkable survival capabilities under conditions that approach those found in deep space. The fragmentation of 3I Atlas would create the perfect opportunity to search for any biological materials that might be preserved within its nucleus. Even if no living organisms survived the journey, fossilized remains or biomarkers could provide evidence that life existed in the alien system where the object originated. The transport network concept also raises fascinating questions about information transfer between star systems. If advanced civilizations exist throughout the galaxy, they might deliberately use the interstellar transport network to send messages, archives, or even technological artifacts to other stellar systems. Objects like 3I Atlas could potentially carry encoded information that we haven't yet learned to recognize or decode. The way 3I Atlas breaks apart might itself contain information. If the object's internal structure was deliberately engineered to fragment in specific patterns under solar heating, the resulting debris field could constitute a kind of message that becomes readable only when the object undergoes thermal stress. This might represent a communication method designed by intelligences that think in geological timescales rather than the brief lifespans of biological creatures. The Galactic Transport Network might also explain some of the puzzling features we observe in planetary systems throughout the galaxy. The unusual chemical compositions, unexpected planetary configurations, and exotic material properties detected by space telescopes might reflect the influence of interstellar material transport over billions of years of galactic evolution. As you contemplate this vast cosmic circulation system, consider that objects like 3I Atlas might represent the galaxy's way of sharing resources and information between star systems. Every interstellar visitor carries with it a sample of conditions from its origin point, creating a kind of cosmic library that preserves information about stellar environments across space and time. This galactic perspective leads us to one of the most profound implications of 3I Atlas's potential fragmentation. What it might reveal about our own solar system, its place in the cosmic community, and how our world might be connected to alien environments in ways we've never imagined. As we approach the deeper implications of what 3I Atlas might reveal through fragmentation, we encounter a possibility that could fundamentally transform our understanding of our own solar system's history. This interstellar visitor might carry evidence that our cosmic neighborhood has been far more connected to alien worlds than we ever suspected. The arrival of 3I Atlas in our solar system isn't just an isolated event. It represents the continuation of a process that might have been operating for the entire 4.6 billion-year history of our planetary system. If interstellar objects regularly pass through our cosmic neighborhood, then our solar system has been receiving visitors from alien worlds since its very beginning. Some of these ancient visitors might have done more than simply pass through. They might have been captured by our sun's gravity and incorporated into our solar system's population of asteroids, comets, and small bodies. This means that hidden among the familiar objects we've studied for decades, there might be interstellar immigrants that originated in alien star systems billions of years ago. The fragmentation of 3I Atlas would provide a template for identifying these hidden alien objects within our own solar system. By studying the chemical signatures, structural properties, and isotopic compositions revealed by 3I Atlas's breakup, we could develop criteria for recognizing other interstellar visitors that have taken up permanent residence in our cosmic neighborhood. The implications of this possibility are staggering. Some of the asteroids in the asteroid belt, some of the comets in the Kuiper belt, and some of the small bodies scattered throughout our solar system might actually be ancient interstellar visitors that were captured during our system's early history. These objects would preserve within their structures samples of alien chemistry from star systems that might no longer exist, but the connections might run even deeper. If interstellar material transport has been operating throughout our solar system's history, then some of the materials that formed Earth itself might have originated in alien star systems. The building blocks of our planet, the chemical elements that make life possible, and even the water in our oceans might include components that traveled across the galaxy from distant worlds. The fragmentation of 3I Atlas could reveal isotopic signatures that match materials found in meteorites that have fallen to Earth. Such matches would provide direct evidence that alien materials have been incorporated into our solar system's inventory of small bodies, and potentially into Earth itself. The implications for understanding our planet's formation would be revolutionary. Consider the possibility that some of the most unusual meteorites found on Earth actually originated as fragments of ancient interstellar visitors similar to 3I Atlas. These alien meteorites would carry within their crystalline structures information about star systems that existed billions of years ago, providing samples of alien worlds that we could study in terrestrial laboratories. The organic chemistry that might be revealed by 3I Atlas's fragmentation takes on even greater significance when viewed from this perspective. If complex organic molecules can survive interstellar journeys and be incorporated into planetary systems, then some of the organic compounds on Earth might have alien origins. The chemical precursors that led to the emergence of life on our planet might include materials that formed around distant stars. This possibility raises profound questions about the uniqueness of terrestrial life. If the organic chemistry that led to life on Earth included alien components, then the boundary between terrestrial and extraterrestrial biology becomes much more fluid. We might all carry within our bodies atomic and molecular components that originated in alien star systems. The magnetic properties of materials revealed by 3I Atlas is fragmentation might also provide insights into our solar system's magnetic history. If the object contains materials that preserved magnetic field signatures from its journey through interstellar space, these signatures might include records of our solar system's magnetic environment from periods when our sun was young and magnetically active. The gravitational influence of 3I Atlas and other interstellar visitors might have played subtle but important roles in shaping our solar system's architecture over billions of years. Close encounters with interstellar objects could have altered the orbits of planets, changed the distribution of small bodies, and influenced the long-term dynamical evolution of our planetary system. But perhaps most significantly, the study of 3I Atlas and similar objects might reveal that our solar system exists within a stream or current of interstellar material that has been flowing past us for billions of years. Our sun's motion through the galaxy might carry us through regions of space that are particularly rich in interstellar visitors, creating periods when our system receives more alien materials than usual. The fragmentation of 3I Atlas might reveal whether the object is part of such a stream, and whether we can expect more similar visitors in the coming years. If 3I Atlas represents the leading edge of a group of related interstellar objects, we might be entering a period of increased interstellar visitor activity that could provide unprecedented opportunities to study alien materials. The timing of 3I Atlas's arrival, during an era when humanity has developed the technological capability to study interstellar objects in detail, might not be coincidental. Our solar system's movement through the galaxy is carrying us into regions of space where such encounters become more common, potentially opening a new era of interstellar archaeology. As you contemplate these hidden connections between our solar system and alien worlds, consider that every atom in your body might carry a cosmic history that spans multiple star systems and billions of years. The fragmentation of 3I Atlas might reveal that the boundary between home and alien is far more complex and interconnected than we ever imagined, and that our planet's story is inextricably woven into the larger tapestry of galactic evolution. This brings us to the most mind-expanding possibility of all: what the fragmentation of 3I Atlas might teach us about our cosmic future, and how humanity might eventually join the vast network of interstellar travelers that connects the galaxy. As we reach the culmination of our exploration into what 3I Atlas might reveal through fragmentation, we arrive at perhaps the most profound implication of all: what this interstellar visitor might teach us about humanity's own cosmic destiny. The lessons locked within this ancient object could provide a roadmap for our species' eventual expansion beyond our solar system and into the galaxy at large. The successful billion-year journey of 3I Atlas demonstrates that interstellar travel is not only possible, but potentially common throughout the galaxy. While the object might not represent deliberate spacecraft design by an alien intelligence, it proves that materials can survive the harsh environment of interstellar space for geological timescales while maintaining their structural integrity and chemical information. This survival capability provides crucial insights for human interstellar mission planning. The materials revealed by 3I Atlas's fragmentation could serve as a library of tested designs for interstellar durability. By studying which materials and structures survived the object's billion-year journey, we could identify approaches for building spacecraft and probes capable of similar endurance. The fragmentation process itself would reveal how materials respond to thermal stress after extended exposure to the interstellar environment. This information would be invaluable for designing human artifacts that must function reliably after centuries or millennia of interstellar flight. We could learn which engineering approaches remain viable over cosmic timescales and which are likely to fail. But the lessons extend far beyond simple engineering considerations. 3I Atlas represents a successful model for information transport across galactic distances. The object has carried detailed information about its alien origin across thousands of light years and billions of years, preserving chemical, structural, and isotopic signatures that tell the story of its birth environment. If humanity eventually develops the capability to send interstellar missions of our own, we could apply similar principles to create spacecraft that serve as time capsules and ambassadors. These missions could carry detailed information about Earth, human civilization, and terrestrial biology to other star systems, where they might be discovered and studied by alien intelligences millions of years in the future. The chemical preservation demonstrated by 3I Atlas suggests that even delicate organic molecules can survive interstellar journeys if properly protected. This opens possibilities for biological interstellar missions, spacecraft that carry preserved samples of terrestrial life, genetic information, or even living organisms in suspended animation to other worlds. The fragmentation of 3I Atlas might reveal whether complex information storage systems could survive interstellar travel. If the object's internal structure contains patterns that encode information beyond simple chemical composition, it could demonstrate that advanced data storage techniques are viable for interstellar communication across cosmic timescales. The galactic transport network that 3I Atlas represents points toward a future where humanity becomes part of a vast, interconnected system of material and information exchange between star systems. Rather than viewing interstellar travel as isolated missions to specific destinations, we might eventually participate in a galaxy-wide circulation system that continuously moves materials, information, and perhaps even life forms between worlds. This network perspective suggests that successful interstellar exploration might require thinking in terms of contributions to galactic evolution rather than simple destination-based missions. Human interstellar missions could be designed to enhance the galactic transport network, leaving beneficial materials and information in strategic locations where they could be discovered and utilized by other travelers. The ancient age of 3I Atlas, traced back to cosmic noon, demonstrates that successful interstellar travelers can preserve information about cosmic history across geological timescales. Humanity's interstellar missions could serve similar archival functions, preserving records of our solar system's current state for discovery by future galactic civilizations. But perhaps most significantly, the study of 3I Atlas and its fragmentation might teach us about the types of information that are most valuable for interstellar exchange. The chemical signatures, isotopic ratios, and structural properties that make this object scientifically fascinating could serve as templates for designing human contributions to the galactic information network. The fragmentation event, if it occurs, would also provide insights into natural methods for distributing information across large volumes of space. Instead of concentrating all information in a single massive spacecraft, we might learn to design missions that naturally fragment during their journeys, creating distributed information networks that are more resilient to loss and more likely to be discovered by alien intelligences. The success of 3I Atlas in preserving its alien origins through a billion-year journey suggests that humanity could eventually contribute our own unique perspective to the galactic community. Our particular approach to science, technology, art, and philosophy could be preserved and transported to other star systems, enriching the cosmic conversation between intelligences. The timing of 3I Atlas's arrival during humanity's technological adolescence might not be coincidental. As we develop the capability to detect, study, and eventually intercept interstellar visitors, we're becoming participants in the galactic transport network rather than passive observers. This transition marks humanity's graduation from a purely local to a galactic perspective on existence. As you contemplate this cosmic future, consider that every technological advancement we make, every scientific discovery we achieve, and every cultural evolution we undergo might be preparing us for our eventual role as interstellar travelers and contributors to galactic civilization. The fragmentation of 3I Atlas might provide our species with crucial lessons about how to participate successfully in the vast, ancient, and ongoing conversation between intelligences that spans the cosmos. The study of this ancient visitor reminds us that we are part of something much larger than our solar system or even our local galactic neighborhood. We exist within a universe where information, materials, and perhaps consciousness itself flow between worlds, creating connections and possibilities that extend far beyond anything we can imagine from our current earthbound perspective. As we reach the end of our journey through the extraordinary revelations that could emerge from 3I Atlas's fragmentation, remember that we are living through a historic moment in human exploration. Right now, as you listen to this, telescopes around the world are tracking this ancient messenger from cosmic noon as it races through our solar system, potentially carrying within its nucleus secrets that could reshape our understanding of the galaxy itself. Whether 3I Atlas fragments during its solar approach or continues intact on its journey back to interstellar space, this remarkable visitor has already expanded our vision of what's possible in the cosmos. It has shown us that our solar system is connected to alien worlds in ways we never imagined, and that the galaxy might be filled with a vast transport network that moves materials and information between star systems across cosmic time. If this exploration of cosmic archaeology and interstellar mysteries has opened your mind to the profound connections that bind our world to the galaxy at large, make sure you're subscribed and hit that notification bell. Because the universe is revealing its secrets to us at an unprecedented pace, and the next cosmic visitor could arrive at any moment with even more extraordinary revelations about our place in the galactic community. Sweet dreams, and remember, you are part of a species that is finally beginning to understand its cosmic heritage and destiny. The atoms in your body might have traveled across the galaxy before becoming part of you, and the future you're helping to create might someday send its own messages to worlds beyond the stars.